We're recording now, and this is today we're going to go over skills task 3, and then on Thursday, I'm trying to decide which of these, I'll ask you guys which you want to do more, text analysis or machine learning. I don't know, what do you think?
The both are in the R, right?
Text analysis, so social network analysis is in R, machine learning, text analysis would be in Python. Machine learning it depends. If I do probably be in R. Yeah, the PCA or hierarchical clustering I would do in R. Yeah. So I'm still deciding. I think we need to do text analysis because we spend so much time on it. I'm not sure. Anyways, if you have a preference, let me know. So anyways, like for the final, let me just go over to syllabus real fast. Okay, so second assessment grades are up. I graded the skills tasks 1 and 2. I did like 7 points and 8 points, so that the two of them together 15 points. But if you didn't finish those, like please, you can still submit them. Just submit them. Review 3, and then your attendance. So that comprised the 30 points. For your final assessment, 40 points, right? 5 points again for attendance, which begins today. Review number 4, which you're preparing for next week, right? That's due Sunday night, based on the articles that you've selected for module 4. Task 3 and 4. So task 3 here is going to be the social network analysis, what I'm showing you today. I've redone it. It's not going to be the rhesus monkeys. It's going to be the author keyword or the actor keyword networks. And then task 4 will either be text analysis or machine learning, probably text analysis, I guess. And then routine project. So we'll talk about this more on Thursday as well, but it's 10 points for the draft, 5 points for the final. And let me go down to the schedule. So we've got 3 weeks left. This week we're doing tutorials. Your module 4 video is due on Sunday. We'll spend next week doing those reviewing your videos. I really like these articles that we picked. I think two of the articles are using clustering, so it's unsupervised clustering, and then 4 of the articles are actually using prediction, but they're using it all for different things. So anyways, I think these will be it'll be a fun week. And then your project video draft is due the Sunday after that. So basically, you've got 2 weeks to submit your project video, right, which we will spend the last week of class looking at. It'll be very similar to these video reviews, but it will be your projects, right, your data, your analysis. We'll look at, and then so that's 10 points, right? Graded very similarly to these, except that it's you know, what project that you came up with, like data that you're applying these methods to. And then if you get some feedback, when you get feedback about this, then you'll have time to resubmit it for an additional 5 points. So here you'll get whatever percentage you got on this, you'll get that or higher as you revise it. If you get like a score on this that you're happy with, then you don't have to revise it, and I'll just give you the proportional points, right? The same percentage. And then these skills tasks will just be due at the end of the semester. So any questions on any questions on the calendar? We haven't talked about this project lately, so with that. Is anybody who has like data for the project? Okay. Who knows what data they want to get but they don't have it yet? Okay, and who's like, what's data? Okay, so you should definitely have your data, and hopefully, like some of you, if you're using this network analysis code, like you'll be, I'm hoping that some of you can use the code that I present today to do your project if you're doing active keyword networks. Like if we talk about that, and that's what you want to do for your project, today's code will be, have everything that you need. Right? If you're doing something different, then let me know, and maybe I can help you out if you need some kind of help with the coding. So, okay. So that's a schedule on the calendar. Any questions about like grades or final term grades? What's coming up? Okay. Okay, so I'm recording. We're recording this. Today, and I'll upload this to YouTube at the end of class. So we'll have this as a tutorial for task number 3, which is the social network analysis. So I'm not gonna. You'll do 2 of these, right? You'll do number 3, and then whatever we decide to do for Thursday. I went back and redid the social network analysis. The code and data you can see here. There's a folder here that says layouts optional. I'll kind of explain what these are, but when you do this task, you only need these 3 files. So this file just has the requirements, like what you need to do for the task. Like this is the code in R, and then this is the data. So what I'm asking you to do in this task, let me open these up. So here's a list of stuff to do. Right? So the main thing though is that I want you to construct your own actor keyword network. Right? So I'll show you what this is. I have an example of it, but I want you to construct your own version of one. It's pretty easy to do, but I'll give you an example, and then you'll upload that into R. So first of all, you need to create this network. So this is the actor. I'm saying actor keyword, right? But the actors could be authors, right? It could be if you're doing a network for journals, right? The actors could be a journal, not a person, right? And then the keyword could be like the keywords in the articles, right? The keywords in the articles that you were looking at, like the 5 article keywords at the bottom of the page. So it could be like what journal and keywords if you have like say 20 articles in a bibliography, right? Like what journal was it in and what were the keywords? And in that case, if one journal article has 5 keywords, then you're going to have that journal in there 5 times with a different keyword, right? So it could be a journal and an article keyword. It could be what this is the professor and their area of interest, right? From a department website. So I think I've shown you this before. This is from like University of Washington sociology department. So if you look at the faculty here, right? So here's the professor, here's the actor, and here are the keywords. So I just went down this page. This is, I mean, I did this like several years ago, so there are new people here. But anyways, so in the actor column, let me put here. So like you constructing this network is part of the exercise, right? Not just running the code. So here's the actor, right? Zach Almquist, or here's one, Catherine Beckett. So I put Catherine Beckett here, and then Catherine Beckett's area of study, criminal law and punishment. There's criminal law and punishment, right? Human rights. So she's added some things have changed since back when I did it, right? But this is the idea. So if Catherine has 1, 2, 3, 4, 5, 6, 7, 8 keywords, then Catherine's name would be here 8 times with the different keywords. Right? And in this column, you put the actor. In this column, you put the keyword. And this is an edge list. Right? These are all the edges in the network between the authors and the keywords. But when you put it in a network, it's actually going to be all connected, because the important thing for these keywords is that you have a closed set of keywords, right? Or that you have enough like repetition between the keywords and different actors that it's actually a network. Otherwise, you just have like a bunch of dyads that aren't connected, right? So you can think of like any kind of this is called a bipartite network, where you have 2 different modes. Anything where, right, you can be a professor with research interests, it could be a journal with like, you know, keywords, but it could be something else too. Trying to think what's something like a non-academic example where you could do this, actors and keywords. Or people in organizations, right? It could be like people in the membership in organization. Could be KIMEP students in the club that they are members of, right? Yeah, it could be students in the courses that they take, right? So you just want to have enough overlap, enough students taking the same courses that when you put this up in a network like this, they're connected. So, you know, do something fun. I mean, you're gonna like when you run the analysis, you're gonna do the clustering. And if you get some fun results with this, so the more time you take to build a quality network about something that's interesting or that you care about, you know, the more interesting or fun the results are going to be. Okay? So first of all, you build this network, and it's just 2 columns with actor and organization or actor and keyword, whatever. Right? So then once you've built this in Excel, then you have to save this as a CSV file. So this is like one little particularity about R prefers working in CSV files. So you can save as, and then you go down here and choose this. Right. So once you've built your Excel file, you can save it as a CSV UTF-8. .csv is a comma separated values file. You save it as that. And then when you, so I've already done this. So in my folder here, you can see I have 2 Excel files. They both have the Excel icon. They both have the same name. This one is an Excel worksheet. That's your normal .xlsx file. The second one is Excel comma separated values. That's your .csv file, right? Now, in the example that we did in path 2, I had some code in there where you could just open up the Excel file. This one, I don't have that. I'm having you like change Excel to CSV, and then you can open up. You can also copy and paste the code from path 2 and just open up your Excel file, not bother with the CSV file. But I'm just having you do it because ours preferred file format is CSV. So it's just a quirky thing about R. Okay, so that here, this is the CSV file, right? So you need the code and then the CSV file. So you're gonna construct your own network in Excel, then you're going to save the network as a CSV file and you'll import that into R, right? So here, I've opened up the code. Make sure that your directory here, if you save the code in a folder and then you double clicked on it, the default directory should be the file where your code was saved, right? So hopefully this is the same. If you need to change the directory, you can use this, like unhashtag this and put your, whatever directory is. But hopefully you won't need that. And you can just double check the directory again. So that's fine. Because you want to be able to find all these files, right? And then import libraries. This is only going to use the iGraph library for now. So if you've already installed iGraph, you just run this one. If you haven't installed it before, delete that hashtag, run install packages, right? And then run library, and then put that hashtag back up there because you only need to install it once. Right? But every time you open the code, you need to run library. So you run iGraph. Okay, and then you need to import the edge list, right? This is the CSV file. So edge list, we're reading the CSV file. Mine did not have a header. So right, so I just started making the list. I didn't put a header like actor keyword, right? From row 1, I just started putting the data, right? So in that case, that's an example of a file that does not have a header. So here header equals false, right? And that's, if you put header equals true, then it's going to read that first row and has like the variable names. So here header is false. And then I'm going to read this in. I'm just going to call this edge list. So the edge list, right, here it is. It's the data from that Excel file. And it's just going to, if you don't have a header, then R just automatically names your variables v1, v2, v3, so on and so forth. So this is your edge list. Just to check, what's the data format for this edge list? So you can check this in Python. You do this by using the function type to check what the data type is. In R, you have to use the function class. They use the class instead of type. Anyways, class of the edge list is just going to be a data frame. So this is verifying that when it reads in this data from a CSV file, it reads it into an object called a data frame. So, okay. This part here, you may or may not need, right? So the way that I constructed this, I put a first name and a last name, and I wanted, when I do the network, I want to grab the last name as the node label, right? I don't want to put like Robert Crutchfield. I just want to put Crutchfield, right, as the node label. So I'm going to grab this and I'm going to partition on the space and take the last name to be the node label, right? And then this is going to be the other node label. Probably if you would just prefer to like manually input the node label, right? For example, say like you're putting in a list of journals, right? And then the journal names are really long, right? So in that case, instead of the full journaling, you might just want to use like an abbreviation, right? Like Journal of East Asian Studies, just put like JEAS, right? Something like that. It'll be easier. And then you don't need to worry about the labels. And in that part, you can just like skip this part, right? And don't worry about having them. So if you want to, you put the data in like this, and then you want to use something abbreviated or abridged for the node label, let me know. If it's not like the person's last name. If you want to do something else, let me know and I'll help you code it. But basically, like, so that's what this is doing. It's taking the last name, right? So I just grabbed all the last names, And then I'm adding those to edge list. Right. So I did that using R code. What you could do, if you want to do this manually, is just when you make the Excel file in the beginning, you can just make this third column like the abbreviation for this node. Right. So this will be like the node label for the left, and then you can do another one if you want to do node labels for the right. So you just have to think about like how you want to label these nodes. Like when you collect the data, just be thinking about like, you don't want your node labels to be like super long, right? Okay, so now we're going to construct the bipartite network. What is a bipartite network? Bipartite network is a network where you have two different kinds of nodes, right? In this case, it's like professors and the things they study. So you have got two types of nodes, and we don't allow edges between the same type of nodes, right? So this kind of edge is not allowed. So in a bipartite network, you can have green to red, green to red, green to red, but not green to green and not red to red. Right? That's a bipartite network. So in your edge list, make sure that it's bipartite, because all of your edges are like one node type to another node type. Right? So, this creates a network. You have to just make it into a, yeah, so this creates a network, and there it is, G. So I'm calling the network, I'm creating the graph from the edge list using this edge list here, and the ties are directed. They are not directed, right? They're undirected ties. And so G here is it's an iGraph object. E means, let's see, and attribute name. Okay, so I took 2 and 3, the second and third column. This is the keyword, and that's the author's last name, right? So all of these are like keywords to author's last name, but it's not directed, so it doesn't matter. It could be the opposite direction too. And I've got 45 nodes and 89 edges. And I have one attribute called name, which is going to give me the name of the vertex. That's just on there. So, so that's my network. Okay. But so far, iGraph does not know that this is a bipartite network. So far, iGraph does not know that this is the name of a keyword and this is the name of an author. It doesn't know that yet. All it knows is these are text, right? So to make a network bipartite, you have to add an additional column with true and false, a Boolean column where one mode is going to be true and the other is going to be false, right? And that's how iGraph is going to know that this is one class of nodes and that's another class of nodes. So how do I do that? I'm going to add in this function, this variable type. I'm going to add this variable type to my graph. And what's type? If name is in the third column of the edge list, right? What's the third? The third column of the edge list is the last name, right? The professor's last name. And name here is just the name of the node. So if the node name is in the name of professors, right? So this in thing is a Boolean test. Like, is this object in this list? Yes or no, right? So if is deviance and social control in the list of professors' names? No. Is Crutchfield in the list of professors' names? True, right? So it's going down all the vertex names, and if the vertex name is in the list of professors, it returns true, and if it's in the list of keywords, right, it will return false. So this is a logical test to see if the vertex name is in this third column, is in this list of professor names. So true values will be professor names, and false values will be keywords, right? And I'm saving that as one column of data to this variable called type, which I'm adding to the graph. Okay? So I'm going to run that, and now you can see. Now this B is here, right? Now it knows it's by part type, whereas before it didn't. Right? So now it knows it's by part type, and and the attribute name here is the node name, but type here is whether it's professor name or not. Right? So now it's by part type. Okay, so let's look at these attributes. You can, right? So G is the graph, and then this is iGraph notation. So the V parenthesis is iGraph's way of saying I want to grab the vertices from this graph. Right? So V is for vertices or like nodes, and then these nodes have attributes. So the name attribute. So in R, if you have a data structure and it has attributes inside, how do you get those? You put the $sign. So if you want to know like the names of vertices, you can look at $sign name, and that gives you the names of all the vertices. If I do VG type, what is it going to show me? It's another column of data. What was the data type of type? So remember, type is coming from this logical test of true and false, right? So if I look at type, it's just going to be a list. Right? It's just one column of data, true or false, right? But that's what this needs in order to tell me are the nodes of one type or another type. So, anyways, this is just how it knows that you have bipartite networks. Okay. So now that I've got a bipartite network, now I want to take it apart. Right? I just made this bipartite network, but now I want to project. So I can create two bipartite projections, an actor network and a keyword network. Right? So this is my network over here. This is the bipartite network. And let's say these are actors, the green ones, and let's say the red ones are keywords. Right? So if I do a projection into the actor space, then I have two nodes, 1 and 2. And as long as 1 and 2 are connected to a common keyword, then I'm going to put a tie between those. So this is the projection of this bipartite network into the actor network. And then if I want to do keywords, I can also project this bipartite network into the keyword network. Right? And then, so is there an edge between these ones? Why is there an edge? Why would there be an edge between keyword A and B? Keyword A and B connected. Yeah, because they both have a tie to a common actor, right? So in the keyword network, they would also be connected, right? So this is a projection into the actor network. This is a projection into the keyword network. So this is how a bipartite network you can either preserve the bipartite network, or you can project into either space. So in the actor network, how are actors connected? Actors are connected if they share a common keyword in the actor keyword. In the keyword network, how are keywords connected? They're connected if they share the same actor in the actor network. So, so if you take this function bipartite projection on G and then you create BP, save it to BP. What is BP? BP is actually a list of networks. BP is projection 1. Right? Is this the actor network or the keyword network? The keyword network, right? We got keywords to keywords now. And then the second network down here is the actor network. You have actors to actors, right? So bipartite projection, it takes a bipartite graph and then it gives you two graphs. It gives you the keyword network and the actor network. So now we've got three graphs. We've got the bipartite, we've got the actor, and we've got the keyword. Right? So we're all done making graphs. Now let's look at them. So okay, so I'm gonna save the projection 2 as the actor network. I'm gonna call that actor. Right, this is projection 2. Right, this is projection 1. The projection 1 is the keyword network. Projection 2 is the actor network. Right? So here, and this bipart projection is BP. So BP $ projection 2, that's the actor network. So I can save that as actor. And you can see there's the network right there, right with the actors. And then I've got, you can see the names, right? These are the names of the nodes in that actor network, and I can plot it. Right, so it looks ugly there, but that's the actor network. And then I can define the keyword network. So it's the BP $ project 1 or projection 1, save that as keyword. Here's a list of the keywords, nodes, right? And I can plot those. Okay. So I'll come back and I'll make those prettier later. But I also want to plot the bipartite graph, the original graph. Okay. So the bipartite graph, so I just want to explain this code because I use this code like throughout the rest of it. First I'm creating the layout, the graph layout. Each time, so check out this keyword network. Let me just run this again. So look at where the keywords are right now. Down here is like criminal law and punishment is at the bottom, right? If I run this again, it changed, right? The graph structure changed. The graph layout is random, not random, but it's probabilistic. So every time I run the plot on the network, it's going to change. And sometimes I don't want that to happen, right? Sometimes I want to like get a plot and I want to stick with it because I want to change the color or I want to do clustering and color the nodes or something, but I don't want the network to change every time, right? So in order to, if you plot it once and you like the layout, you can save that layout as a separate file. And then every time you plot that graph, even if you change the node colors, you can keep the same layout so that you can make multiple copies of the same graph in the same layout. Just change, maybe you want to change the node labels, maybe you want to change the colors, maybe you want to change something, but you want to basically keep the graph in the same layout. Right? So that's what this is. So here, I want to use a Kamada Kawai layout on the bipartite graph. I've already done this, right? And I saved that as a file by layout, right? So I've already done that once, and so you can see in my file here, I've got all of these files here are graph layouts or something. Some of these are not layouts, but anyways, here's the my layout, right? I've already got that. I already did it once, so I don't want to do it again because it messed up my layout, right? So the first time you do this, you'll need to run this. The first time you do the layout, you'll need to run it. And then you'll need to save it. But once you've run it and you've saved it, then hashtag those. Don't use them again. Otherwise, it'll change the layout again, right? So the first time you do it, run it and save it. And then it'll save that layout to this file. And then you hashtag those. And now that file is saved in your folder. And now you'll run by layout equals read RDS, right? And that will read the layout file, which is saved in your folder, okay? So some of you will run into trouble with this. If you run my code just as it is, you know, you may not find this file. You're going to have to unhashtag this, run it first, save it, then hashtag those again, and then run the read, right? And then so if you've done it once, then you can just leave these hashtags, comment it out, and then just run it like this. So each time, like you're going to read the layout in, and then you can plot it. And when you plot it here, note, so the by layout is the name of the layout. In this file, sorry, when you plot, now note that layout, I'm using the by layout in order to plot it. So if you don't want to mess with all this layout stuff and you don't care that it's like changing all the time, then you would just delete the layout here, right? And then every time you plot it, it's just going to plot it differently. But I'll show you why like having the layout is nice. You know, because sometimes you want to compare, you want to keep the same layout, right? But just change node color. So okay, so I've done that. So that's what here in Moodle, that's what I'm including in the layouts, right? Like the by layout, the actor layout, the keyword layout. There's some other stuff in here, other things like that. The reason I'm including it as optional is because if you're doing a network for, right, if you're creating your own edge actor keyword network, right, these layouts are not going to be relevant for you, right? You're going to have to create a new layout for your own network. If the only reason I'm including those is if you want to run this code on my network, if you want to use the layouts that I already created, then you can download those and use them, right? Just to run the code, just to see it works, right? But for you, if you have a different file here, you're going to have to run all these layouts yourself the first time. So I hope that's not too confusing. If you run into trouble with the layout, let me know. I'll be happy to help you with it. So here's the layout. I just read that file in from here by layout. And now I'm going to plot the bipartite network using that layout. So there it is. It's compressed. It's kind of hard to see. So I'm going to plot the same thing again, but as save it as a PDF file. Okay, and I'm saving that as bipartite.pdf. So if I go in here, go down to bipartite PDF. Right, and there I have the network. Right. So this is the bipartite network. Here, the green nodes are professors, the blue nodes are keywords, right? And then in the plot, you can also change the colors and stuff. Right? And you'll recognize this layout, right? I've shown you this graph before, and it's the exact same layout as the one I showed you before. And that's how you preserve the layout. It's really annoying, like when you lose your layout and then you have to normalize them all again. Okay, so I'm going to do, I have the same code in front of all of these, right? Because the actor network, so I've done the bipartite network. Now I want to do the actor network and the keyword network. It's the same, right? So the first time you run it, you're going to have to unhashtag this, run the actor layout, save it, and then hashtag this again, right? So here's the actor layout and the actor network, right? And then I'm going to plot this to a file, a PDF called actor. So there's the actor network, right? Those are the professors who have common research interests, right? Then the keyword network, same thing. And then I'll print it out. It's called keyword. Okay, so there's the keyword network. So you've got the bipartite network, you've got the actor network and the keyword network, right, all separated. Okay, so we printed those three networks. So that is these, right? You're going to construct the bipartite network. You'll plot the graph, color each mode differently, give the plot an appropriate title, print it as a graph. Here, project the actor and keyword networks, plot each graph, give it an appropriate title, print the graph, right? So that's, you've got three graphs now. Okay, so next step is the community detection. So we're going to generate actor communities. We're going to use a function called SpinGlass. It's just it's an algorithm for calculating it's for clustering networks. Right? So I've got the same code here. Why? Because community, like clustering algorithms on networks are also probabilistic. Like if you run it 3 times, you might get 3 slightly different answers. Okay? So when I run it on the actor network, whatever clustering it gives me, I want to save that clustering so I can apply it to all future graphs. Right? It's the same as a layout. Right? It's not a physical layout, but it's a categorization of like the clusters. Right? So when you run this, you're going to hashtag this, run SpinGlass community on your actor network, and save that as SG actor. Then you're going to go down here and save it, right? And then you'll hashtag these again. And then if you want to access it, you can read it after you saved it. And then I can show you the membership attribute of this SpinGlass will tell you which nodes are in which clusters, right? So you can see here. So let me show you the actor. Oops. Okay, so what this is doing is it took the, let me plot the actor network real fast. Okay. So let's look at this 77566, right? What this is SpinGlass clustered this network, and it identified 7 different clusters. Okay? And what it's doing is, one by one, Crutchfield, Beckett, Grimes, Burstein, it's labeling which cluster it's in. Okay, so let's see. These 4 over here, 5 should probably be in the same cluster. Right, so let's look at a Quinn. So Quinn is 19, 20, 21. How many? 25, 26, 27, 28, 29. So anyway, it's hard to tell with this. Quinn and Kaiser, where's Kaiser? Kaiser is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 14. Okay, so 6 is this group over here. Right, so 1, 2, 3, 4. That's 1, 2, 3, 4. So that's Burstein. Okay, Burstein is included in that group. Where's the next 6? Thoreau is included in that group. Right, the next 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 6, 4, 5, 6, 7, 8, 9. Harris. Or maybe there's actually one after this one. Hamilton. Right, Hamilton is over here. Right, so anyways, these are the memberships of the nodes in the clusters, right? And then this is saved. This is actor membership. So, but this is not in the network yet. This is in an object called SG actor. It's a spin glass object. So we need to save these memberships. Actually, we want to use these memberships to color the nodes in the network. Right? We want to color the nodes in the network by these cluster IDs. Right? So, so we're gonna. So we've created these. So we want to plot the clustered actor graph. So we're going to plot the graph again, but now we're going to remember we're going to use that actor layout, right? Because we want the layout to be exactly the same with the actor network. But for the vertex color, we're going to color it using the membership. Right? And I'm just adding 2 in there because I don't like the first 2 colors. It's just it's going to color it. You can just put in actor membership, and then it'll be like green, blue, something. Right? This number just kind of shifts the color matrix down the palette. It doesn't matter. So, and then the labels are going to be the actor names, right? So if we run this, now it's hard to see here. Let me see if I zoom. Right, but now they're colored by the cluster. Okay, so I want to print those out. I'm going to call that actor community or actor com, I guess. This could have probably done a better name. Right, so now I've got these are, this is the actor network clustered by, clustered. And then we're gonna do the same thing with keywords, right? So you get the keywords and the keyword membership here, only 5 of them, I guess. And then we'll plot that and save it as keyword community. And that is here. Right, so you can cluster the keywords as well. So we've got legal studies, criminal law, punishment, human rights, blah, blah, blah. Right? So you've clustered the actor network, you've clustered the keyword network. But any one of these things could be an application, right, in your research. Right? Maybe you don't care about actors, you only care about keywords, right? If you're doing a semantic analysis, you simply use the actor keyword network to get to the keywords, right? Or maybe you only want to do a social network analysis. You want to see like who are the main actors in this field, but you don't really care about the keywords. You're just using those to get to the actors, right? So you don't always care about all of these graphs, right? Like if you care more about the social side of it, you're using this bipartite graph to get to the social network, right? If you care about the semantic side, you're using the bipartite network to get to the semantic structure. Right? So you may not always care about all of these. Right? I'm just kind of showing you what you can do. Okay, so now we've done community detection. You've plotted each graph, colored the nodes according to their respective communities, and you printed those. So you've done those 2 graphs. Lastly, we'll do this centrality measures. I put a little bonus thing in here called correspondence analysis. It's not required for task 3, but I just want to show you what it is. So correspondence analysis was popular in the 80s. It does something very similar to what these bipartite models are doing, but instead of connecting things in a network, it's using this correspondence matrix or this matrix to plot them on a XY axis. Right? So I just wanted to show you what correspondence analysis is, because sometimes you encounter it and it's very similar. So you don't have to run this, you can just skip it if you want, but I just want to, you need to, if you want to use this, you'll have to install the package. But you can just run it and save it. I just saved it as a CA, correspondence analysis PDF. I'm just going to show you this too. We don't have to focus on it very long, but it's an alternative. It's an alternative visualization, right? So it's an alternative visualization to the network, but the clustering is quite similar, right? So you still see Hamilton, Shiro, Kaiser, Stovall over here in the theory group, right? You see Crutchfield and Wise down here in deviance, and right. So this is what people did before they were doing this, right? And you still see this in like papers in the 80s. Pierre Bourdieu's book Distinction uses correspondence analysis to show how elites in Paris. He uses this to show like to illustrate the concept of habitus, which is like do you know have any of you heard of habitus? Habitus. It's kind of like a social version of an ecological niche, right? So like what's the ecological niche of a squirrel? Yeah, they live in a tree, they go up and down trees, right? Telephone poles, right? They eat nuts and other stuff, they put their nuts in the trees. But so habitus is kind of like that, but in the social world, right? So if you're kind of a Parisian, you live in Paris, you're kind of upper class, upperly mobile, you've got some money to spend, you know, then right, you drink wine, you eat cheese, you go to the opera, right? So he would take these kind of surveys and basically do a correspondence analysis to show like here are certain groups of people and like the stuff that they do, right? And here's some other people and here's the stuff that they do. He would kind of map it out as like an ecological map, right, of Parisian society, like. And you can see like, okay, like elites are doing this, and like middle class is doing this, and lower class is doing this. But you could do the same thing with our actor keyword network, right? If you put in like a person and like what kind of stuff they like, you know, like what kind of media do they consume, or what kind of foods do they eat, right? So you could do the same thing. But I just wanted to show you like this is getting at the same thing. Correspondence analysis is getting at the similar thing as clustering. The disadvantage of this, I think, the reason why I think network analysis is better is because this shows you proximity, but it doesn't show you relationships, right? Whereas the bipartite analysis, the bipartite network, it shows you proximity and clustering, but it also shows you like specifically who's connected to what, right? And that's missing from this graph. Plus, it's all like on top of each other. It's kind of hard to read. So I just threw this in there because it's. I think network analysis kind of replaces correspondence analysis. I think it's a better method. So back to the networks. So let's do centrality measures. I calculate all 4 measures for both networks, right? So for the actor networks, I calculate the degree centrality. I sort them. And here's the histogram. Right, so we can see Bernstein has the highest degree centrality, Crowder second, Grimes, Hedwig, right? This is degree, like who has the most interest or the most connections in the actor network. Here's the distribution. But I just threw this stuff in here because it's like everything. We do the same thing for betweenness centrality. We do the same thing for closeness centrality and eigenvector centrality. These are like the 4 main types. And then I'm just including this code in here in case you decide to use it later for whatever you want. So here's the 4 different degree centralities for keyword network, right? Right. But in terms of output, I'm just going to ask you to create one graph. Right? So here for centrality measures, just choose one kind of centrality measure for either the actor or keyword network. Okay? So you've got 4 centralities for the actor network, 4 kinds of centralities for the keyword network. What I chose is between the centrality, the actor network, because I think that predicts who's going to be department chair, right? So I use between the centrality, right? But if you're interested in the semantic network, right, in the keyword network, and you're interested in like which terms are most popular, right, then you would use like degree centrality in the keyword network. You do something else, right? So you don't have to use the same thing as me. But just choose one kind of centrality measure on one kind of network, and then plot it. and I create this red to white raster, right? So to indicate high centrality nodes. So you have to create like a raster is like a set of colors, right? A series of colors, because if I have, some people have like very high centrality between the centrality, some people have very low. So I want to map this raster to the continuous between the centrality measure, so that if you have low between the centrality, your node is white, right? And then the highest between the centrality is like bright red. And then kind of everything in the middle is like some shade of pink, right? So that's, you can create these rasters to kind of correspond to continuous measures, so that when you visualize the nodes, you can see like, oh, high between the centrality, those are bright red, white means like low, and then pink is kind of in the middle. Right? So this is like very, very technical stuff that you have to think about when you're doing like node colors or shading, right? You could, if I was printing in a journal, if I was printing in a journal that did not allow color printing, then I would do a white to black raster, right? Where the middle tones are kind of gray tones, right? But like black is very, or the other way around, right? Like black is like low level and white is very high, something like that. So, okay, so color vectors for random graph centrality. Here's my palette from white to red. And I kind of normalize it based on the cuts in my, between the centrality for the actor. So if you're going to adapt this to something else, like not between the centrality of the actor, but maybe degree centrality for the keyword, right? Then you would replace this BET actor between this actor with whichever centrality measure you're using. So anyways, all these centrality things are here. So here's like degree keyword, between this keyword, closeness keyword, right? Eigenvector keyword. So I'm using between this actor to normalize the raster here. Okay, and then I'm going to plot it. Now the vertex colors are this, right? It's the raster corresponding to that actor between the centrality. And if I plot it here, and then I'm going to plot it again, or save it as a PDF, and I call this, what I call this, actor between. So, right, and there. So these are the high between the centrality folks, and you can see some of these are pink, and then some of these peripheral ones are basically 0. Okay. So part of the, there's a certain amount of like math involved in like plotting these networks, right? Like deciding, for example, like maybe there's too many edges and you want to filter it, right? You only show like nodes that have a certain number of ties or more, right? Or maybe you want to make the node larger depending on how many, like it's in degree or something like that. But there's always a certain amount of math involved to like decide exactly how are you going to rescale the node size. Sometimes you can't just use degree because like the graphics, if this like the normal size is 1, but then the degree is like 20, and now your node size goes from 1 to 20, like the node is going to be like bigger than the page, right? So it has to be like some percentage of the node size, and you have to like weigh it, based on the maximum or whatever. So there's always some kind of ad hoc adjusting that goes on if you want to like play with node and edge colors and attributes. Okay, so that's that. That's the centrality measure, right? And then upload your documents, right? So upload the Excel or CSV file, upload your R code, and upload these 6 PDF files, right? For task 3. Bonus material not included is the correspondence analysis. And last but not least, I want to show you the block model, Again, this is not part of task 3, but I've talked about block models, and I just want to show you what it is because it's a very elegant way to visualize the network. So what's a block model? Again, this is not required for task 3. Block model is a simplification of your network, and I wish people, have you ever seen you've seen some of the papers that we've looked at where they put it like a picture of the network and it's just like a big, huge network, right? It's just like, it looks like a hairball, right? And visually, like there's nothing there's no useful information to extract from that photo. They're just trying to say like, look, it's a network. Like, check, got it. Like, because was there some better way we could have visualized this to like help us, give us some intuition, right? So I think block models are helpful in this way. Suppose you had a network like this, 5 nodes. Suppose we had done clustering algorithm on this, and 1, 2, and 3 are in one cluster, and 4 and 5 are in another cluster. Let's just say. Okay? Then the social matrix, right, for this network. Another way to represent this network is we put 1s or 0s, right, for the number of ties, right? So 1 to 2, there's a tie. But 1 to 1, we're just going to put 0s on all the way down the diagonal. Okay, 1 to 2, there's a tie, so that's that. Right? 1 to 3, there's a tie, so that's that. 2 to 3 is a tie, so that's here. 1 to 4 has a tie, that's that. Well, 3 to 5 has a tie, so that's that. What about 5 to 1? No. 5 to 2? No. 5 to 4? Yes. 4 to 2? No. 4 to 3? No. And 1 to 5? No. Okay. So this is our original social matrix, right? That's a matrix representation of that graph. Now, 1 to 3 we're going to call A, and 4 and 5 we're going to call B, right? These are just sets, clusters, right? So the way you build a block model is you're going to reduce all the nodes in each. The reason we call it a block model is because we're going to block off the matrix by the clusters. And now, how many sectors do we have in this matrix? 4, right? I'm going to reduce this sociomatrix to a simplified sociomatrix whose nodes are these. So it's just going to be AB by AB. I'm going to collapse everything inside of A. I'm going to collapse it to a single node. Right? So how many ties are inside of A? This would be AA, right? How many ties are inside of AA? 6, right? So there's 6 ties. How many ties are inside of A to B? 2. How many ties are inside of BA? 2. And how many ties inside of B to B? 2. Yeah. So now I have this new social matrix. A, we'll say this is the green one. This is A. And this is B. Now, A to A, that means inside of A, within this cluster, there are 6 ties. Actually, I double counted, right? Because like 1 to 2 and 2 to 1 are the same. So we should actually divide these. Right? We'll call this 3, 1, 1, and 1, right? So inside of A, there are 3 self-referential ties, right? So like 1 to 2, 2 to 3, and 3 to 1, right? So we can write this as 3. So inside of A, there are 3 ties pointing to itself. Inside of B, there's 1 tie pointing to itself. And from A to B, there's 1. And from B to A, there's 1, right? All that. This is a block model. This, much more simplified. It makes a lot more sense when I show you here. Like, so intuitively, we already have blocks, right? We did clustering on the actors and we did clustering on the keywords, right? So here, what you have to do to make this work, though, is, so here's the keyword. Here are the keyword clusters, right? You have to go back to this. Okay. And let's look at the, what was the, okay, so here are the keyword clusters, right? They're colored by cluster. Deviance and social control is number 4, right? That's here, this orange one, right? What label would we give that orange cluster? Social legal studies, criminal law and punishment, human rights, deviance and social control. Something around law, right? I think I just called it deviance and social control. Like this green one. So what you need to do is take this graph, these communities, and then label each of those communities. Like give a label to each of those clusters. And then using your keywords, you have to figure out like which cluster is like 1, which cluster is 2, which cluster is 3, 4, 5, right? So you have to like match them up, right? Using the keyword name and the membership, right? So the first, this deviance and social control, that's going to be in the 4th cluster. Stratification, that's going to be in the 3rd cluster, right? So you have to figure out like what order they're in, right? From this, and then you create labels, right? So you add your labels in that order. So here, deviance and social control. Actually, that's 4. Anyways, yeah, so these labels, they might not be in the right order. But anyways, yeah, so you put the keyword labels here, and then if you want to do the same thing for actors, you can put the actor labels here. So then, anyways, you create those labels, and now you are going to add those labels to your graph. Create the block model. Plot it, and here I'll save it as a PDF. Do the plot layout and the PDF. All right, here's the R-type block. Right. So this is the bipartite model where all the actor nodes, all the blue actor nodes have been reduced to these the clusters, right? So they're clusters. I label these as like the green ones are the people. So there's the social demographers, there's the sex and gender folks, right? There's the demographer and methodology folks, there are the deviance and inequality folks, the institutionalists, and 2 of the clusters were actually individuals, right? So I just left their names. And then with the keywords, the keyword blocks, I have the stratification and race, the family, sex, and gender keyword cluster, I have the political economic theory cluster, right? And now you can see like, what do the deviance and inequality folks study? they study demography and methodology, and actually, I think I didn't get them in the right order, right? But anyways, you can see like, okay, they would study this thing and this thing, right? And the edges here are like, how many connections do you have, right? Like I could have put a weight there, but anyway, this is the block model. So I've reduced. It's kind of a double block model, right? Because I've done a block model on the actors and I've done a block model on the keywords, and then I put them together in a bipartite network. Right? And I think this kind of a map is much more intuitive, right, than this original. Where's my original bipartite network? Right. So compare this and this. Right. With a block model, you can go from this to this. And this wasn't too bad. This was like manageable. I could have still put that in the paper. It's like less than 30 nodes or something, right? But, you know, if I'm looking at a network with like thousands of nodes and tens of thousands of edges, no point in putting that in the paper. It's pointless, right? But if I have clusters that are meaningful, right, this is actually pretty cool. This is pretty intuitive, right? So anyways, I just included the code in there. Again, the block models are not part of task 3, but I put it in there so you could kind of just get a feel for it, and you can use the code in the future if you're interested. By the way, you could also do, this is the block model on the bipartite network. You could also just do the block model just for the actors or just for the keywords as well, right? But I wanted to kind of put them together. So, okay, that's task number 3. I'm going to stop the recording. And if you have any questions, you know, about if you run into like errors or problems with these kind of hashtag, like comment out, uncomment, like layouts or whatever, let me know and we'll solve it. Oh, by the way, like I don't mind if those of you who wanted to use this for your project, like you can also use this analysis. You can use this analysis for task 3 and then just do your video off of this, right? So you don't have to like do the analysis twice. I guess what I would say is if you're going to do this analysis for your project, then I want you to create a new actor keyword network, right? If you're not going to use this analysis for your project, then I think that's asking too much, right? So you can just use my network to satisfy this task, right? So say you're going to do your final project on something else, then just use my actor keyword network. You don't have to make your own. But if you're going to use this for your final project, then please do make your own actor keyword network and run the code on, and then you can submit it for both task 3 and the project. Is there in the lights on? Okay, all right.